Okay, hello everyone, welcome back. So now that we've understood fermions, we're going to move on to gauge theory. We're going to warm up with Abelian gauge theory before moving on to non-Abelian gauge theory for the final part of the course. So okay, what is gauge theory? To understand this, we need to first understand what a gauge symmetry and what gauge invariance is. So I'm going to talk about that for a little while. So what is gauge invariance and what is gauge symmetry? This is section 7.1 in my lecture notes. So let's start from the simplest example. Let's consider a theory with a global U1 symmetry. So for example, the Dirac action is a good one to consider. So recall the Dirac action. The Dirac action takes the form S as a function of psi and psi bar is the integral d4x psi bar I d slash minus m psi. And maybe I should just make explicit that everything here depends on position. So I mean psi bar x, psi of x. Okay. Now, this theory is clearly invariant under a global U1 phase rotation, which I write down for you. Is psi of x goes to e to the I, or rather goes to psi prime of x, where psi prime of x is related to psi of x by a factor of e to the I lambda. Okay, so I'm rotating psi by a phase, and I'm calling the rotated psi psi prime. And similarly, of course, psi bar of x goes to psi bar prime of x, which is e to the minus I lambda psi bar prime of x. Because psi bar is mostly psi conjugate. Okay, so the theory is clearly invariant under that. You can see that psi and psi bar always appear together, and so the two phases cancel. All right. So I want to emphasize here that the parameter lambda that appears here, this phase parameter, is just a number. It's constant in space-time. It does not depend on x. Okay? Indeed, that is why we call this a global symmetry. It's a global symmetry because this parameter lambda is constant. And I want to also emphasize one more thing. Both psi and psi prime are physical field configurations. This is such an obvious thing to say that normally you wouldn't even say it, but let me just emphasize it again. Psi and psi prime are both physical in that they could both happen. You could examine a configuration of field psi or psi prime, and you integrate over both of them in the path integral. Okay. So this is, again, seems quite obvious, but let me just emphasize it. Okay. Now here's an idea, which I'm going to state without a huge amount of motivation. I'm just going to state it as a thing that we're going to do. So here's an idea. Let's do something different. Let's demand that we have a theory that's invariant under a symmetry where the symmetry parameter lambda varies in space-time. Okay. In other words, let's demand invariance under the following symmetry. Psi goes to psi prime, which is e to the I lambda of x times psi of x. Okay. Where the crucial difference here, of course, is that now lambda of x depends on space-time. Because this symmetry parameter can depend on space-time and has a different name, this is called a local symmetry or a gauge symmetry. I'll use the language gauge symmetry. Okay, so this is the definition of a gauge symmetry. Now, as I'll explain later, the truth is this name is not actually a great name. There's a sense in which it should really probably be called something like a gauge redundancy or something like that. It's probably a better name for it than gauge symmetry. But despite that, that fact, this terminology is extremely standard, and I will call it a gauge symmetry in the rest of this course. Okay. Things that are invariant under this symmetry are gauge invariant. Okay, so let's understand now what is and is not gauge invariant. So first of all, is psi of x gauge invariant? No, psi of x is not gauge invariant, but it transforms in a very simple way. Psi of x transforms to psi prime, which is just an overall phase multiplying psi. But psi is not gauge invariant. Although it has a very simple gauge transformation. Okay, let's look at the Lagrangian again. Let's take a look at the mass term in the Lagrangian. Let's see if that's gauge invariant. So what do we have? The mass term is m psi bar of x, psi of x. Okay. So let's look at the primed version of the mass term. Okay, where we have the primed guys. So the primed version relates to m prime, the unprimed version, in the following way. Psi of x picks up a factor of e to the minus I lambda of x. Psi bar of x picks up that factor. Psi prime of x picks up a factor of e to the plus I lambda of x. Okay. And that's how the primed and unprimed guys are related. Now, of course, these two phase factors cancel. And so we get m psi bar of x, psi of x. Okay. So this mass term is gauge invariant, because it takes the exact same form in the primed and unprimed variables. Okay, so note that this would not have happened if the two fields here, psi of x and psi bar of x, were evaluated at different space-time points, because in that case, these guys would not have canceled. And this suggests that something bad is going to happen when you look at the derivative term, and because the derivative is just really comparing fields at two different space-time points, slightly different space-time points. Okay, so let's look at the derivative term. So, we're going to now run into this issue that has to do with the fact that the gauge transformation is local, that it changes from point to point. So what is d mu psi prime? So d mu psi prime of x is equal to d mu of e to the I lambda psi of x. And if you work out what this is, clearly there's a, let me try to take the e to the I lambda out front. There's a term coming from the derivative acting on the e to the I lambda, which looks like I d mu lambda. And then there's a term here, which is d mu acting on psi of x. Okay. And you see, this looks very bad. Okay. Basically, not only is this term not gauge invariant, so obviously the derivative is not gauge invariant, it's not gauge invariant in a sort of very bad way. There's this ugly inhomogeneous term coming from the fact that lambda can depend on space. And there's no really obvious way to get rid of this term. You can't cancel it against anything immediately. And so the point is, as we've written it, this Dirac action here is not gauge invariant. Okay? It is not invariant under a local U1 symmetry. Okay, so how do we fix this? Okay. So a good analogy for sort of sophisticated students like yourselves who study general relativity already is to remember that you've had this problem before. Okay. Do you remember when you took general relativity, you had a vector field? You had like a vector field v mu you tried to take a derivative of v nu, and then this was all bad, right? It was bad because this thing didn't transform like a tensor. And this was confusing, and you had to deal with it. And the way in which you dealt with it was you invented a new kind of derivative. You invented what was called the covariant derivative, and that solved your problem. Okay. The same thing is happening here. The formal way to say it is d mu psi does not transform like psi does. It transforms in a bad way. We have to fix it, and we're going to have to invent a new kind of derivative to do this. We're going to invent something called the gauge covariant derivative. Okay. So here we go. Let's define the gauge covariant derivative. And that's defined with a capital D. Okay. So capital D mu of psi is defined to be d mu plus IE A mu of psi. Okay. So what's happening here? A mu here is a new field. Okay. It's a new thing that I've made up. It's a new vector field, which is called the gauge field, or if you'd like, you can also call it the gauge connection. Sounds slightly fancier and more intimidating. Okay, so GR students might be tempted to compare this gauge field to the Christoffel connection, which you studied in that course. It's really a very similar idea. The analogy becomes even closer when we do non-abelian gauge theory in the next part. But for now, let's consider it as its own entity. It is the gauge field. Okay. And also, there's this factor E here. I've chosen to take this factor E out just for convenience. This is purely a definition of the normalization of A. For convenience, I've taken a factor of E out of this thing. But this defines the gauge covariant derivative as well as the gauge field. Okay. So now, here's what we're going to do. We are going to demand that d mu psi has a nice gauge transformation property. Under gauge transformations. Okay. So in particular, we're going to demand the following. We're going to demand that if you take d mu psi and you do a gauge transformation, d mu psi goes to d mu prime psi prime, where the gauge derivative, the gauge covariant derivative also transforms because it has a field in it. And I'm going to demand here that this is e to the I lambda of x times the unprimed guy. Okay, so this is my demand. So note what's happening here. Psi has a particular gauge transformation property. I am demanding that d mu psi have the same gauge transformation property, meaning that it transforms like a phase. This kind of thing should seem kind of familiar to you from GR. Okay, so this is my demand, and I'm going to call this demand equation star. All right. In particular, there's no awkward inhomogeneous piece in this transformation. Okay, so let's see what we need a mu prime to do to make this happen. Let's expand everything out. So in particular, I have here d mu prime psi prime. So what is this? So by the definition of capital D mu, this is partial mu plus I a mu prime. And from the definition of psi prime, this is e to the I lambda of x times psi of x. Okay. So let me now just expand this out. So I'm going to expand. And what I find is that this becomes e to the I lambda of x. Now the derivative acting on the lambda brings down a factor of e to the I d mu lambda. There is, of course, the I a mu prime. And finally, there's the d mu acting on the psi of x itself. Okay. And now, let's recall that I want this to be equal to an overall phase factor times the unprimed d mu of psi, which means that I want the following to be true. So this bit here is my demand. from equation star, I want this to be equal to, oops, just d mu plus i.e. a mu, acting on psi of x. Okay. So from comparing these two things, we can see that this is going to work out if we say that this is how A transforms. It transforms so that A mu prime equals to A mu minus 1 over E d mu lambda. Okay. So this is the required transformation property of A mu prime. Let me also put next to it the transformation property of psi, just to remind you, because the two are correlated. One induces the other. Okay. So this is the transformation of the gauge field. How the gauge field transforms under gauge transformations. It's an important formula, so I'll let you take a second and stare at it. It transforms like the gradient of a scalar quantity, lambda. Okay. So if we have this, then now the gauge covariant derivative transforms the way that I wanted it to from my demand star. So note that now that we have this gauge covariant derivative, we can use it to do what we want. So for example, if we now look at the kinetic term in the Durham Lagrangian, except that we build the derivative with the gauge covariant derivative and not with the normal derivative, the partial derivative, then everything is okay, right? So let me just go through this carefully. So if we look at everything primed, then, well, the primed psi bar is psi bar of x e to the minus I lambda of x. And then we have here gamma mu. And by construction, d mu of x is e to the I lambda of x times d mu psi of x. And now these two things are numbers, so they pass through the gamma matrix and they annihilate. And just as we wanted, we do get that this thing is invariant. Okay. Okay. So with this, we can now write down a fully gauge invariantized Dirac action. And that just takes the form d4x psi bar of x I d slash, where it's capital D slash now, minus m psi of x. So this is a fully gauge covariant or fully gauge invariant version of the Dirac action. Okay. Notice that this came at some cost, though. We had to invent a field A to make this work. Okay? And this is the price of gauge invariance. There is no way to do this without inventing a new field A. Okay. Okay. So now that we have this new gauge field A floating around, we should ask what more we can do with it. So to understand this, I'm going to first note that because d mu psi has a nice gauge transformation property, so does the combination d nu psi. And so it makes sense to consider the commutator of two covariant derivatives. Okay? In other words, I'm going to take this and subtract from it the same thing with the mu and the nu flipped. So let's consider the gauge covariant derivative d nu psi. So what is this? If you expand it out, you'll see that there's a term here coming from the commutator of the partials. And then there's a term coming from the commutator of of these. This whole thing multiplies psi. Okay. And then if you work this out, you can see that this whole thing just becomes I times E partial mu A nu minus partial mu A mu acting on psi. Okay. So notice that this commutator of derivatives, okay, acting on psi is not actually a derivative at all. It's just a number multiplying psi, because this thing here is just a number. Let's call this number I.e. f mu nu. Okay. In other words, I have defined something called f mu nu to be partial mu a nu minus partial mu a nu. This is the definition of the field strength of the gauge field. Okay. Now, purely abstractly, we know that f mu nu is actually gauge invariant. Let's understand why that is. Well, the point is, from the construction, we built f mu nu to be the commutator of two covariant derivatives. Now, let's consider acting with this equation on psi and doing a gauge transformation on both sides. Okay? So I take this and I act on psi, and then I gauge transform both sides of this. Well, the point is, I know how the gauge covariant derivatives transform. They just transform with an overall phase. And furthermore, I know how psi transforms, and psi transforms an overall phase, which just goes straight through the f. Sorry, let me write it like this. And so I can just cancel the e to the I lambda from both sides, and this immediately implies that f mu nu is gauge invariant. Okay. Now, the truth is, you could also just immediately conclude this from looking at this form of f here. You can just transform A using the known gauge transformation property of A and just verify that this thing is gauge invariant just directly. I'm doing it in this abstract form because this abstract way of doing it is actually useful when we get to non-abelian gauge theory. Okay, so now we have a combination of derivatives of f, which is gauge invariant, called the field strength. Now, it's not hard to convince yourself that if you just take random derivatives of things like d mu, a nu, blah, 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 these are not gauge invariant in general. Okay, it's only the particular combination d mu a nu minus d nu a mu, which is gauge invariant. So let's now try to write down the most general renormalizable gauge invariant action involving a mu and psi. Okay. Okay. So it turns out the most general such action is the following. Okay, so this is it. Now, the first term is gauge invariant because f mu nu is gauge invariant. And this is really a kinetic term for the gauge field A. Okay, it's like dA squared. This is the kinetic term that gives the gauge field A dynamics. The second term we've talked about already. Now, the third term might stress you out. The third term here looks a little weird. Okay. Now, it's weird for at least two reasons. The first reason why it's weird is because it has an epsilon symbol. This totally antisymmetric Levi-Civita tensor. Okay. Which means that it breaks parity and time reversal. Okay. Another reason why it's weird is it turns out that this is a total derivative. And you can check that for yourself. It's a fun thing to do. Verify that this is a total derivative of the form d mu k mu, where k mu is something you can work out. What that means is it does not obviously contribute to the equations of motion. So you might think that it doesn't contribute to equations of motion or Feynman rules. Okay, so you might think it's not interesting. It turns out to be very interesting indeed. There's some references in the notes if you're interested in learning more about it. And this is what is called the theta term. Okay, it turns out to be quite important, particularly in the non-Abelian case. But we're going to just ignore it. We're going to say that it's 0. We're going to set it to 0 by demanding parity invariance. Okay, I'm going to demand parity. If we demand parity, then theta must be basically 0. And for that reason, we can exclude this from consideration. And we're not going to stress about it anymore in this particular course, although there's a lot of beautiful physics hidden inside of it. Okay. And thus we conclude that the most general gauge invariant and P invariant action is then the following thing. Let me write the next line. So this is the most general gauge and P invariant. And this, of course, is exactly the action of QED, of quantum electrodynamics. You studied this extensively in your QED course. So I want to stress here, we were led to this purely from symmetry principles. There is nothing else that we could have written. Okay? In other words, let me say it in the following way. This is fixed completely by gauge invariance. There is really nothing else that we could have written down. Okay? You can add more powers of f or more powers of psi, but that breaks renormalizability, as you can check. And anything else at this order in mass dimension is not gauge invariant. So the action of QED is completely fixed by gauge invariance. Okay, so next we're going to discuss some classical aspects of this theory before discussing the quantum aspects of it further.